Hello and welcome. So in this video, we will continue to take a look inside the current control system. So this is where the core of the vector control or field-oriented control algorithm is implemented. In the last video about our current control system, we saw what was inside the hardware input and input scaling block. This is where the speed and position estimation, since it is a sensorless scheme, we have to estimate or what motor's internal state is looking like based on various machine parameters. So that is what this block did. So we saw in detail about how it is calculating the actual rotor speed. So without any sensor, we are estimating the rotor speed and rotor position as well. So these are the measured currents from the sensor. So we will connect two sensor in the A phase of the motor and B phase of the motor. We will give it to the ADC of our launch pad, analog to digital converter. So it will convert to digital value and we will get that value and we will perform some scaling to convert to per unit and subtracting the offset. So that is what we did in we saw in these two blocks. Now the measured currents and the position, the estimated position, the estimated speed and the reference current. So this reference current is coming from the speed control system. So we will give the speed reference as a user. We will give it the speed reference. For example, this motor should run at 1400 rpm or something like that. So we will give that 1400 rpm and it will calculate. So this system will calculate the ID and IQ reference currents. So to achieve this 1400 rpm, I need these two ID and IQ currents. So this is we saw in the second video about how it is exactly doing this. So it is generating the reference current for the induction motor. Okay, so we have the reference current, we have the measured so IAB current for A phase, current for B phase measured in per unit. PU stands for per unit. The position in per unit, the speed feedback. So and we have the ID and IQ reference current. So let's go into the current control system. So in which you can see the measured IAIB current is transformed to ID and IQ currents. So through the Clark and Park transformation. So the Clark transformation transforms the IAIB, the stator frame currents, into alpha beta frame, where the alpha and beta are two space vectors spaced 90 degrees apart. So in this ABC, A and B are separated by 120 degrees. In the alpha beta frame, they are separated by 90 degrees. In the DQO frame, they are separated by 90 degrees, but these two are time varying quantities, but these two are not time varying quantities. That is, they are not oscillating by nature. Okay, so this Park transform requires a very crucial variable theta. So which when open loop mode uses the speed reference for an approximate estimation for the theta. When in closed loop mode, it uses the flux observer position. So the closed loop, the theta is coming from here, the position per unit, so which is in turn coming from the flux observer. So you can see it is going into the position. So in a closed loop mode, we are using the estimated flux position, flux observer's position. In the open loop mode, we are approximately using the speed reference to generate the theta. Okay, so we use this theta to calculate sin theta and cos theta, which are required by the Park transform to transform the time varying alpha beta to DKO, which is not time varying. In normal condition, it is like a DC quantity. This lookup table is nothing but one giant table with when given theta, it has already computed sin theta and cos theta value. It has been stored in a table. So it will just see for this row take that sign value. So it will directly read from the memory instead of computing the sign of that value. So usually sine and cosine is computed using Taylor series expansion. We will approximate sine and cosine with Taylor series. So which is pretty expensive to run in the hardware. Since already this system is complex, we don't want to overload the system, so we will use a lookup table. So let's go into the current controller. You can see the reference current. So in a PI controller, regularly what we will do is we will feed the reference current, we will feed the actual currents. So the difference of that will give the error, how much error is there. and then that error will be multiplied with some gain. For a PI controller, it will be multiplied with Kp and Ki. Then P term and I term, proportional term and integral term will be added, and then it will give the output. So that is exactly what is happening here. So we are giving the reference current here and the ID feedback. So this is ID feedback is nothing but the transformed currents. That's all. Our measured currents is transformed to the DQ frame. So this is our actual motor currents. So the actual motor currents in the DQ frame is compared with the reference current. So it will be, as I said, this will be subtracted to get the error signal. So the reference minus the actual current is subtracted to get the error, and inside this is an inbuilt block. So it will multiply the error with Kp, the error with Ki, then add the term and then give to the Vref. So this block also we covered in the speed control system in detail what each of the input does. Okay, so if it is in the closed loop mode, we are taking this PA controller output value, then giving it to the Vref, the reference voltage that we need to produce with the inverter. So the gate pulses for that reference voltage is given from the PA controller. So if it is in the open loop mode, we don't use this. We directly give the VD open loop. We are setting the initial integral term value to be whatever goes out on the Vref. So that is simple PI controller which takes ID reference and ID actual current and ID reference current and produces VD reference. And then similarly for IQ. So we are taking the IQ reference current and IQ feedback current, subtracting the same thing. So initially at open loop, this value is set to be 0. The Vref, VDref and the VQref is given to a DQ limiter. So we also looked at this block in detail, why we need to use this particular block to limit the voltage. We cannot just simply clamp. So if your VD, the reference voltage needed, that is this voltage will be applied to the inverter gate pulses, right? So if this voltage is very large, you may saturate the machine or damage the machine. So if it is excessively high, so you cannot just simply clamp the voltage to whatever maximum value you can produce. So it will not preserve the phase relationship, that is the angle relationship between the direct axis and quadrature axis component. So we'll use direct axis and quadrature axis limiter. So please watch that video for more detailed look at what this block is doing. Okay, so this dref and qref, if it is below the maximum value, then this exact value is propagated outwards. So this saturation value is exactly equal to the reference value. Then the quadrature axis reference value is passed through the out in the qsat port. Okay, you don't need to worry about this. So this is the field weakening control. If you want to run the motor beyond the rated speed, we will usually go with field weakening control. If it is not on the field weakening control, so if it is on that, then we will use these value, and then it is given to the ID field weakening control. But if this is false, then this value, the 0, is going out on the ID field weakening control. So if this is 0, then we are adding nothing. This is only for if you are running at beyond the rated speed. Okay, then other things are for debugging. To watch these values, we are giving it to some flags and giving it to one port 3 for debugging. This torque estimator, which is also used for debugging, we cannot we don't use any torque sensor in our shaft, right? So we estimate the amount of torque with this block. So we will give all the induction motors parameters and then give the stator direct axis, quadrature axis and the speed. So right click on that and press help. You can see all the formulas of this block. So this is the electrical torque produced at the shaft. So in the rotor we are producing this much electrical torque, but there are some losses, the friction loss and the windage loss, all that is subtracted. So after that the mechanical torque is what we are getting. So this electrical torque which is actually produced internally in the machine, in the rotor before any losses, is 3 by 2 times pole times magnetizing inductance by rotor inductance into flux linkage of the rotor direct axis and stator's quadrature axis current. This 3 by 2 factor is since we are working with the DQO frame, so that factor is coming from there. So this pole, if you increase, this is not pole, this is pole pair. So north and south constitute one pole pair. So if you have more poles, you'll have less speed but more torque will be there. That is why this is in the numerator. So if you increase the number of pole pairs, so for example 4 pole, 8 pole, the torque will be higher but the speed will be lesser. And this magnetizing inductance is nothing but how much effectively the magnetic path of the machine is there. So if you have large air gap, so it will have the reluctance of the air gap is very high, so the inductance will be less. So if you have large magnetizing inductance, so if you have very less air gap, so more flux will pass through, so there will be more inductance, and then the torque, electromagnetic torque produced in the machine will also be very high. So this constitute, so this fraction effectively subtracts the leakage flux. So this is a scaling factor. So if the rotor leakage inductance is very high, the electromagnetic torque will be less. So if the magnetizing inductance, so the magnetic coupling between the stator and rotor is very strong, that is what this LM signifies, then your electromagnetic torque will be very high. And this is the most interesting term. The flux linkage, this lambda RD stands for the d-axis flux linkage in the rotor. So the flux linkage and the quadrature. So the lambda RD is multiplied with stator's IQ current. So let's say this is our rotor. So this is our stator's current. So the stator's magnetic field we are resolving into two components. The direct axis component, which is flux producing component, and the quadrature axis component. If you want the motor to have high torque, that is high twisting force, you have to make this quantity, that is the quadrature axis quantity, much larger. So it will produce a larger twisting force. So if you pull the motor from this direction, so this is the stator, this hand is the stator. So if you pull the rotor like this, you will not be getting any torque. The rotor has to spin like this. So you have to get the much torque from the quadrature axis. So how much current you have to maximize? So that is the aim of the FOC. You can maximize the quadrature axis component to maximize the torque. This direct axis flux and this quadrature axis flux, so will produce the maximum torque. So the direct axis and the direct axis of the rotor and the direct axis of the stator will not produce any torque. So and the quadrature of the rotor and quadrature of this will also not produce any torque. So this direct and this quadrature will produce the maximum, it will produce the torque. The torque producing component are these two. So if you have once again, so if you have I stator quadrature axis current is much larger, then your torque will also be very high. So if your rotor flux is also stronger, then also your since your magnetic coupling is high, the twisting force will be maximum. So this is how the electromagnetic torque is calculated, and the electromagnetic power, the electric power. The electric power is calculated by the electrical torque into mechanical speed. So this power is calculated by this formula. So TE into, so this is simple, right? This is very analogous to electrical term. So P equal to voltage into current. So in mechanical terms, voltage and current are torque and speed. So this is just for debugging purposes. We are not using in the core FOC algorithm. Okay, we got the VD ref and the VQ ref by multiplying the current error with the gains, and then after DQ limiting we got the VD ref and VQ ref. So that ref we are transforming into alpha beta frame. So this block accepts the input in alpha beta frame or ABC frame. We are giving it in the alpha beta frame. So in the alpha beta frame we are feeding the V alpha V reference alpha and V reference beta. We are using space vector modulation. There are a lot of other modulation. We are using SVPWM just because it utilizes the DC bus much effectively. Okay, so now we are getting the A, B, C, three phase currents in the stator frame. Okay, so this V alpha, V beta is going through this inbuilt block to generate the VABC in the space with the space vector PWM modulation method. So we are giving the VABC ref to the output scaling block. So that concludes our control system. The core FOC is over. Now we'll just scale the input and give it to the inverter. So you can see the VABC ref is given to the output scaling. This is nothing but our actual values will range from 0 to +1 to -1. So it will range from like that. So what we are doing is we are multiplying by 0.5 is nothing but dividing by 2. So this -1 to 1 we are dividing by 2 and shifting the entire waveform up. So maybe I can quickly show in the graphing calculator. So let's say we have sine of, I am multiplying, so you can see this ranges from -1 to 1. So the difference is actually 2. -1 plus 1 is 2. So the peak to peak value is 2. So I am multiplying it by 0.5. So which reduces the amplitude by half, and then I have to add 1.5 here. So what I did is I divided and added some value 0.5. So our entire waveform got shifted up and scaled down. So now the waveform ranges from 0 to 1. So our digital signal processor, the launchpad understands only digital value, right? Between 0 to 1. So that is why we are doing this scaling. And then this enable flag. So if you want to disable the gate pulses, you can set the flag to high or low, so it will stop the gate pulses to the inverter. So we are converting the data type, so this is not much important to us. Okay, so this PWM duty cycle and PWM enable is muxed into one signal and going to the inverter. You can see here there is a two stacked squares like icon, so which means this, as I said in my previous video, this will run differently in simulation mode or in the code generation mode. So in the simulation mode, if you double click on that, we can see in the inverter simulation mode, we are just getting these inverter signals, the VABC after scaled, we are getting that and giving it directly to the duty cycle. So this just if it is enabled, so if the PWM input is enabled, we are virtually making it the signals go through the output port 1. If not, then 0 will go through the duty cycle, so the entire gate pulses will stop. It will be 0. So virtually we are doing this, and this same DT block ensures are these signals and this enable flag or sorry, this 0 value and this are same data type. So if it does not, then at compile time it will give a error that these two are not same. This is how it will behave in the simulation mode. So virtually when you are simulating entirely within MATLAB, you don't have a physical inverter, right? So it will mimic the inverter's function, that gate pulses stopping virtually here. But if you double tap, you defaultly will go into the simulation mode. That is because the entire thing is in the simulation mode. So if you want to go to the build and deploy mode, it will change to the hardware mode. So you have to click on this inverter. You can see this inverter signal can go. This code generation block is grayed out. That means this is not active, but you can see how it is there. So in my last video, I explained how to generate the PWM waveforms. Kindly watch it to understand this gain block and what these modules are. So this is essentially a hardware specific module for my for this particular board, F2837 series board. These are the three for three phases we are using this block, and you can double tap it and change the module 1. So we have some 12 modules. Here it is 18 module, but depending on the processor, for 3 processor it is common, so they are giving 18 modules generally, but for our F2387 it is actually 12 modules. So this will generate the PWM at specified pins. So that pins can be seen here. Go to the hardware settings here. Okay, select your board, Delphino Launchpad, target hardware resources, EPWM. You can see PWM 1A is assigned to GPIO 0. 1B, we are not using 1B here. They are not using it. So for inverters, upper switch and lower switch, we will usually give for a R phase. For example, RYB. For R phase, we will give 1A to the upper switch, 1B to the lower switch. So these waveforms will be complementary of each other. So you can double tap on this. As I said in my EPWM video, the last video. So in that EPWM modules have two channels. Each module has two channels. There are 12 modules. So two channels for that. Then there are 24 output channels. We are enabled EPWM 1A. This is similar to the simulation mode. You see here, if the enable is true, then the inverter gate signals is multiplied with the gain. So this gain is the counter period. So if this enable is true, then the signals is multiplied with the gain and then going to the three phases. If it is false, if the PWM is disabled, then 0 is going to the all the three pins. Okay, that covers the inverter. So that inverter gate pulses is actually generated, and then this virtual inverter feeds to virtual induction motor with all our parameters. So if you want to entirely simulate it in the simulation, so you can use this. But as far as the hardware is concerned, so this block will generate the duty cycle and it will stop there. So then it will feed to the motors, it will feed to the actual inverter. So in my case, I'm using an intelligent power module which has the IGBT, hyper IGBT with gate drivers inbuilt to one module. We will give these gate pulses to the intelligent power module. Then it will produce the appropriate voltages at the motor terminal. The appropriate currents will flow. Motor will respond and will read the IA and IB. Then it will give. That is how the loop closes. But as far as the hardware is concerned, but if you are in the simulation mode, you can see it is pretty simplistic. So the duty cycle is going to the virtual inverter and motor in the simulation mode. So in the code generation mode, we don't use this. So nothing is there in the code generation mode. So this duty cycle is going to the terminator block. As I said, the actual gate pulses generation ends in this here in the hardware. So but in the software, we are using this simulation, this motor, and we are approximating how a ADC will respond with this sensor measurement. So that is this. In the next video, I think I will cover the serial communication between the host model. So you can click on this host model. It will open this. So you can start the motor. You can use the field weakening mode. You can set the reference speed. So to monitor and control the motor, we will use the host model. So that host model will be in our system, that is laptop. But our actual FOC code, so this entire code will be converted to assembly code and sent to the C2000 launchpad. So that launchpad will be our target. So this is the host, this is the target. So the communication between target and host is through serial communication, more specifically SCI communication. I think I will cover in the next videos. So thank you.